Hi everyone, my name is Anvita Bansal and we are back with another lecture based on stacks. So I'll just quickly check if you guys are able to see my screen. I think we are live now. Okay, so the question that we will be discussing today is largest rectangular area in a histogram. Let me just quickly show you the problem statement. So we are discussing the stack and queue section of our ST sheet. So this is the question, largest rectangular area in a histogram. So let's have a quick look at what this problem is. This is a very good problem, very frequently asked in interviews, and this concept is widely used in building good level problems. So what is it? Let's understand. Find the largest rectangular area possible in a given histogram where the largest rectangle can be made of a number of contiguous bars. Okay, I'll explain you the question. We don't need to read the question entirely. You should have. Okay, so what you're given in this question is you are given an array of integers where each integer actually represents the height of a histogram. I'm sure you know what a histogram is, right? So you're given these heights of histograms. You have to tell what will be the maximum area of the histogram that you will find. So what does this mean? Let's have a look at the test case and then I will explain you. Okay, so I am taking the second test case of this problem, which is 7 2. Let me write it. 7 2 8. This is the array 9 1 3 6 and 5, right? So this is the given array. Now what do you mean by the largest area in the histogram? So if I draw a histogram assuming considering that these are the heights at each index of the histogram. Okay, so let's see what our histogram is going to look like. So this problem you need to understand that what is the intuition behind this problem. Let me just quickly draw the histogram so I will move on to the further topic. So this is, if I can take a bar, just a second, let me take a bar. Pictures, no, shapes, and let me choose a where is that shape? Let us check what can we have it. Let me draw it like this only. Okay, so let's see what we have here is we have a bar with height 7, right? This is a bar with height 7. Next up we have is a bar with height 2. Let us take this bar with height 2. Next up we have bar with height 8, so this will be greater than this. Okay, this is bar with height 8. Next up we have bar with height 9. Okay, this is the one with height 9. Then we have bar with height 1, which is this. Next up is bar with height 3, so this is 2. I'll make it greater than this height, so this is height 3. Okay, then we have height 6, just smaller than this is what I'm going to create. This will be our bar of height 6. And then we have bar of height 5, which is like this. Okay, I will write what are these heights. So this is height 7. This is your height 7, right? This is height 2. This is height 8. And this is height 9. This is height 1, 3, 6 and 5, right? Okay. So what is the basic intuition behind this problem? See, this problem, when you first look at it, it's, if you recall the previous question that we discussed, next greater element, can you relate something? Can you try to get some understanding or maybe intuition? This is the hint I'm dropping so that maybe you can get some intuition behind this problem. What do we actually want? So before we move ahead, let me tell you what do we actually want to find is the maximum area of the rectangle in this histogram. So what kind of rectangles you can find from this histogram if I talk about? So if you see, each bar in itself is a rectangle. Okay, so if I were to calculate total area of each bar, for this it will be 1 9 8 2, because width for each bar is 1, that is fixed, right? That width of each bar is 1 and their heights are varying, right? So if each bar is to be considered, they will be the area, their area will be exactly equal to the height that they have. But there is a possibility to get a rectangle with even greater area. How is that possible? So you can observe that those rectangles, if I can find, see, this rectangle can have width more than its own width. Why? Because this rectangle can sweep area till where? Till here. Why? Because here you're getting a bar, whose height is less than its height. So maximum that you can sweep the area for this particular, just randomly I've chosen one bar, and what I want to explain you here is that if I just talk about this bar, maximum area that it can sweep is till this, right? Only this part towards its right. If I talk about its left, so if I go to its left, I can obviously sweep this area as well. So total this all of this area can be considered for bar of height 2, right? So what area does this bar give me? That is its own height 2 multiplied by total width. What is the width? So this is of 1 2 3 4. If you check, your bar with height 2 can give you a rectangle with total of 8 area, right? So I just randomly picked one bar, and what did I try to see? I checked that if for that particular bar I move in its right direction. So how much far can I move? I can only move until I get a bar whose height is less than its own height, because until I find a bar which possesses a height greater than that current height, right, I can always sweep that area. I can get an area by always extending my arms to that direction. Same goes for left direction. If I am present at this current bar, till what unit of histogram I can go towards left, until I find a bar whose height is smaller than this bar. So that much of width can be consumed, right? And area and total area will be its own height and the total width that I can sweep to my left and to my right. Okay, so I hope the intuition is clear to you. Now what does the question remain? Now the question remains that we must be doing the same thing for each and every bar. One thing that first, I hope you got some intuition. So the intuition behind this problem is that you are actually trying to find the right and the left barrier. Okay, so you can say, what is the barrier? Barrier is that bar whose height is less than your current height. So you can say it has left boundary and right boundary. So intuition is to find, let me change the color of my pen, is to find the left boundary, right, and to find the right boundary. Okay, for a current bar or index of my histogram at which I am present. Okay, fine. Now this is first thing. Second thing is I must be doing this thing for each and every bar, right? I should be doing this thing for each and every bar. So second point on this comes is that do this thing, find these boundaries for each bar. Okay, that is for each index I that you are at. Now next what? Third thing is how to find these boundaries. That is the entire question. So there are few ways in which you can find these boundaries. One way is, now why we are taking stack into consideration is because I told you, like in previous question, what did we do? We try to find next greater element. So if I draw a stack, my stack can tell me that, for example, if I'm talking about this bar, okay, and I iterate over in this entire array. So what I'm trying to find is, you can say, next smaller element. So the next, let's suppose that we have two stacks maintaining left boundary and right boundaries. For example, this is right boundary stack. So what it will be doing is that, as I am progressing, as I am iterating over my array, what I will be doing, I'll be checking that, for example, if I'm at 2, right, my stack should give me what is the next smaller element for 2. So that will be 1 from the stack. Next, same thing I'll do with the other stack. I want to find what is the left boundary. So I'll be iterating from, means first I'll be iterating from I equals to 0 to I equal to n minus 1. For the other stack, I'll be moving from I equal to n minus 1 to I equal to 0, so that I can get corresponding right boundaries and left boundaries for each index, correct? And then I will one by one pick up the left and right boundaries, calculate the width, and width into that multiplied by that height will be my area. But we will not be going ahead with this solution. I have told you, you can try it on your own. Lots of time, many a times when you try to attempt this problem, you come up with this intuition only and you go ahead and try to solve it. But we will be using an optimized method, because a lot of times this particular solution has been discussed. So I want to go ahead with another one in which we are actually minimizing the use of space. Instead of 2 stacks, I'll be using only 1 stack. And when you go ahead and try this solution, you will see we are actually doing this problem in 2 passes. But in this case, we will be minimizing it. We'll be doing it in 1 pass, although we will be doing some steps on our stack. So it is, to be precise, it will be greater than on, but it will not be on square. Okay, so let me now create a stack, and let's do what we are actually going to do with the solution that I have discussed. Okay, fine. So if I talk about the first, now let's start doing this for my first one. Right now I have an empty stack. Cool. Okay, my I is currently at, these are the indexes 0, 1, 2, 3, 4, 5, 6, 7. So what I am going to do, I am going to fill up my stack in such a way that I am only putting the values, the indexes of bars in the increasing order of their heights. What does this mean? So I have this first bar, okay, I have this first bar whose height is 7. Right now there is no other, your stack is empty. You have this bar of height 7. So let's insert it. Actually, I will be inserting indexes, but here I am showing you the height as well as the index. So my height is going to be 7. My index is going to be 0. Okay, so I inserted this value into my stack. Now move your I pointer to the next one, which is I equal to, first it was 0, now your I is at index 1. Now for index 1, what is the height of your bar? It is 2. So you compare it with the top of your stack. So the top of your stack has height 7. 2 is clearly less than 7. So you can see one thing, that for the current value is actually your stack dot top or peak. Okay, so the peak value, when I find while I am iterating, current is actually not, you can wait, see, so my current index is I, idx is actually I, okay, and my stack dot top, if my stack dot peak height, its height is what, if it is less, then I will push that current value. If it is greater than that idx height, so this means that this is my current value in the stack. What is the height of this bar? It is 7. Now next index that I am trying to push is of height 2, but I am not going to push it. The reason is, the next value that I am going to push, let's say interim value, that is of height 2. If I push this value, what will be issue, that I know that the current value that I have currently pushed into my stack is of height 7. So definitely I found a right boundary for my 7. Right boundary is my current index height. Cur IDX is the right boundary for the bar which is present at the top of the stack. So what you are going to do is you will remove that current value current value from your stack. So what was present, let me write, this is the index and this is the height. So this index will be removed. Okay, now you will check what is present in your stack. It is empty. That means the current value was 2 and you were pushing it. You will push it if you find a value smaller in the stack. If not, then you will actually turn out to be a right boundary for the bar that is present at the top of your stack. Since you have no bar present at the top of your stack, it means there is no left boundary for your current value. That means you can extend it till 0th index, right? And there is no left boundary, so you just push it into your stack. So I'll push the index here. I'm showing you index as well as the height of that. Okay, fine. Now your I is at index 2. What is this height? This is height 8. Compare it with the current height. 8 is greater than 2. Yes, it is greater than 2. So you push in the stack. What is its index? Its index is 2 and its height is 8. Okay, next value, your I is at 3rd position now. The 3rd position bar is of height 9. Compare it with the current height. So 9 is greater than 8. So you push this index, which is index 3, with height 9 into your stack. So see, while you are getting greater heights, you are simply pushing into your stacks. Why? Because as and when this means for the values that you're pushing in the stacks, you can definitely extend this least value, that is the last bottommost bar, can be extended till this width that I'm pushing into my stack, right? But as in when I find a value which is less than the top of the stack, that means, wait, the value that is present at the top of your stack has got its right boundary. So now your task is to find its left boundary so that you can compute the total area for this. So similarly, when I pushed 2, I actually computed area for this bar, and the area that max area that I got so far is actually 7. Fine. After which I pushed 2, then 8, then 9. Now my index is at 4. So I am going to compare. Let me erase these. Okay. Now your current index is at 4. Fine. What is the height at index 4? It is 1. When you compare 1 with height at the top of your stack, which is 9, so definitely it means 9 got its right boundary. Right, so start computing the total area that the bar with height 9 can occupy, okay, or possess. So for that, I now know its right boundary, which is the current indexed height. Now let's find out its left boundary. So I know that I am filling up my stack in such a way that the heights are present in the increasing order. So if I remove it from the top of my stack, the next value that I will have a height which is less than my current height, means the height that I just popped. So now I know that I got a left boundary also. So when I got a right boundary, what was its index? Its index is 4. That is the current I. 4 minus your left boundary index is 2, right? So what I'm actually doing is, this is your 4, and when you have found the left boundary for this 9 value, and typically this 9, if you now observe what is the maximum width it can occupy. So if you try to observe that as you go to its left, you found a smaller height, so you cannot extend your boundaries beyond this. Same for its right. If you try to move towards right, you cannot extend your height 9 till this boundary, because you do not have a bar of height 9 or greater than that. So the maximum width you can occupy is 1 only. So how will you compute that width? So the current width is I, which is 4. Left boundary, what is your left boundary index? It is 2. So 4 minus 2 and do minus 1 so that you can get the exact width, that is 4 minus 2 minus 1, you got the exact width, multiplied by your own height. What height did you just remove from the stack? That is 9. So what is your area? 4 minus 2, 2 minus 1, 1. 1 into 9 is your current area. Compare it with the max area you found so far. It is greater, so you update it with 9. Okay, now what? Still your I is at 4 only. You just computed your right, you know that you found a right boundary for the top of your stack, so you removed it, and then you got a left boundary for this value that was present at the top of your stack. Now wait, you found the maximum area, you got it, you updated it. Now what is present at the top of your stack? This is this bar which is present at index 2 with height 8. So now this bar has a height greater than your current height, which is 1. Your current height is 1. Again, the top of your stack has a height which is greater than your current height. So current height is 1. 1 is less than 8 definitely. Now you have this at the top of your stack. So your task, you found area for this bar. I'm making a tick mark. Let me with a blue, I am making a tick mark. That means its area was computed. You computed the area for 9. Now you are checking for 8. So for 8 you got a right boundary which is at index 1, because 8 can extend here, but 8 cannot extend here. So you got a right boundary for 8 which is 1. The left boundary we will check now. So if I remove it from the top of my stack, the next element that I have will have height which is less than 8. So definitely I will get a left boundary, right? So when I get my left boundary, I know it is present at this. Let's calculate the width. So width will be I is 4. And what is your current index? Current index, since I have removed it from the top of my stack, my left boundary index is 1. 4 minus 1 minus 1, that is 4 minus 2, 2 multiplied by its own height which is 8. I just removed this value, right? So you have to make sure that you are computing the left boundary for the top of your stack. You remove it, you pop it, and the next value that you have in your stack will act as the left boundary. So it will contribute to your width using this formula, and the height will be the value you just popped from the stack. So 4 minus 1 minus 1 is 2 multiplied by 8, that is 16. So you got a height of 16 which is greater than your current area, maximum area. Now what? Now you have this value at the top. So at index 1 you have a height 2. It is still greater than your current height. So again you found a right boundary which is this. So your current index is 4. Your right, you remove it from the top of your stack, you find you do not have anything present in your stack right now. So what will be the case? Since you do not have any other value, you will take 4 minus 1. We will do it in this way, that if there is no other value in the stack, you take your index as minus 1. So 4 minus minus 1 will be 4 plus 1, 5 minus 1, 4 multiplied by your own height which was 2. So it will be 8. So if you calculate, this bar will be taking this place 1 2 3 4, total 4 width, 4 2s are 8. So 8 will not be updated here because your maximum is 16. So the current status of your stack is that it is empty right now. There is no other value. Now you do not have anything to compute, so you push your current value which was this height at index 4. So index was 4 and height was 1. And your stack, rest of the values are not present in the stack. Go ahead, this value you find, this height is greater than the top of your stack, you just push it into your stack. Index is 5, height is 3. Same for this, index is 6, height is 6, greater. Now you got a height of 5, it is smaller. So you do the same task again. When you got a smaller height, you are checking what is at the top of your stack. So that means for the value present at the top of your stack, you have found a right boundary which is at this point. So right boundary is there. Now you find the left boundary which is this. Compute the width. Width will be what? See, so the current index was 7, right? So current index was 7 minus your what we were doing, minus that left boundary which is 3, which is 5, right? We are now finding the left boundary, right? For 1 second. Okay, so we were computing for 6, we got a right boundary which was 5, we are finding left boundary which is 3. So 7 minus this 3 minus 1, I think 7 minus 5 minus 1, because this is the index, that is exactly 1 multiplied by its own height, that is 6. So will you update it? No. So you found a height for this bar also. This bar also got its height. This bar also got its height, that was 16. 2 also got its height. We have already, see, we have computed how many heights, how many areas for this bar, area for this bar, area for this. Now we are calculating area for this bar. We have already removed it from stack. We got a left boundary. We computed the area. We did not update because area was not greater than the maximum area. Okay. Now what is your current index? Current index is 7. Height is 5. Now what is at the top of your stack? So at the top of my stack I have index 5, that is with height 3. So current height is greater than this height. So I will insert into my stack. So index is 7 and height is 5. Okay. Now do you have anything to insert in your stack? No. So what is the current status of your stack? I'm drawing just stack here to show what is the current status. So your stack right now has this index 4 with height 1. 4 with height 1. Next is 5 index with height 3. You will observe that these heights will be in increasing order only. And next will be index 7 with height 5. So basically I have calculated area for this also. I have now these left to be find the area of. Now I have iterated over the entire array and still I have some values left into my stack, which only means that their right boundary is actually the end of your array. That means the last index of your array. They can be, all these values can be extended to the last of your array but not to the left, right? Because that is why they are in this order. So let's compute. So we will do one thing. We will make our I go till nth index, right? So that I can compute the width for these as well. So let's say your total index was 7. My I is currently at 8. So the width for this one will be what? Now I am calculating area for this top of my stack. This is the right boundary with index 8. Let's calculate the left boundary, which is at index 5, right? Yes, because this bar can extend its width till this bar but not this bar. So I will be taking this as the left boundary. So 8 minus 5 minus 1, that is 2 multiplied by its own height, that is 5. That will become 10. So 10 will also not be updated. So I found area for this one also. Now remove it from the top of your stack. You are left with only this bar and this is the last bar you want to find height of. Did I find height for 5? No. I have to calculate for 5. So I have removed this one. That was this index. Now I am left with 4 and 5th index. This is still present at the top of your stack. Okay. So for this, let's calculate the height. Remove it from the top of your stack. Find its height, which is left boundary. Your current is 8. 8 minus 4 minus 1, that is 3. 3 multiplied by its own height, that is 9. So area calculated for this also, 9 will not be updated here. Now you are only left with this index, that is index 4. So 8 minus, you remove it from the top of your stack. Stack is empty, so you do subtract minus 1 and then minus 1. 8 minus left boundary minus 1, right? So 8 plus 1, 9 minus 1, 8. Am I doing it right? Yes, 8. Why its width came out to be 8? Because if I see this 1 can be extended till, for this is width 1, 1, 2, 3, 4, 5, 6, 7, 8. So we got the right width. 8 multiplied by its own height, that is 1. So 8 into 1, 8. Still we will not update. So you will finally return this 16 as your answer. So I did this entire dry run on this question. You got answer 16 so that you can very clearly understand what is happening. If I would have just shown you what code we have done, you would have never able to understand so deeply that what we are doing, what is the intuition behind this problem. So I hope now you got this question. Let's have a look at the code quickly now. It's a very simple and small code, only and only if you understand the logic. So there is a stack of type long, everything is of type long. Since I am creating a stack of type long, what is happening is that for here in indexes, you will have to convert them to integer type. So while what I am doing, I am iterating over the array as I told you, and the last index I am taking it to be equal to n. Okay,
then into your stack. If you stack should be filled in the increasing order of the heights. So you are checking for a first check is if your stack is not empty, then you are doing this thing for the case when your if your I becomes equal to n, right? So in that case, even so if your I becomes n, or let's say your stack is still empty, you should actually enter into this while loop and do the thing. So this thing I'll prefer that you try it on your own and just don't directly start coding. You understand the logic and then you try to code yourself, then you will understand why we have written this condition. Okay, fine. Then our main condition was that if we found, so since I am inserting indexes into my stack, so what I'm doing is, this is histis array of this stack.peak is the index. If that value is greater than equal to your hist of I, which is the current height, right? If it is greater, that means for this peak value found a right boundary, which is this, then you go ahead and find the left boundary. So I've written it like this: right boundary will be your current index, your current height is the one that you will be removing from the top of your stack, your left boundary is the one that is present at the top of your stack. And if in case when you, since you are doing a pop operation here, there are possibilities that you will find you have actually removed the last value of your stack. So in this case your stack will be empty. So if your stack is empty, your left boundary, as I told, should be -1, otherwise it will be the top of your stack. Then you calculate area, which is your current height, which I have written here. It should be current height h multiplied by your right boundary minus left boundary -1, and then you update the max area if it comes out to be greater than your current area. And once you are out of this while loop, anyway, for even if you enter this while loop or you don't, you are pushing that current index. That's all. You guys can ask me if you have any doubts. This is a very good problem. Please try to, even if you have not attended the lecture today, you can come back. Once I'm done with this stream, you can come back, and I'll really suggest you to first attempt this question on your own. No need to code. Try to find out the logic. Then you come up at this video and try to understand how I have pushed and popped the values, on what basis, and how have I updated them for each and every bar of this histogram. Then only you try to attempt the code. Do not copy and do it even if you have understood the logic, because why we have done this thing you will be able to understand only once you try to code yourself. Okay, so that was all for today, everyone, and let's wrap it up. If you have no doubts, let me just check if you have any doubt. How to learn C++ DSA, can you share playlist link? Okay, so see, Mukula, I'll tell you one thing, Mukula, that you can, if whether your target is DSA or your target is language, you need to first, you can choose any language, be it C++, be it Java, that's your choice, depending upon how you want to do. If you want to indulge in competitive programming, go ahead with C++. Even if not Java, I myself do it in Java. Then second thing is, if you want to learn DSA can be learned in any language. You should have a grip on your own language. DSA is all about concepts, right? And if you want to actually implement it, implementation way is your language. You can say the mode of implementation is your language, but logic can be understood through any playlist. For example, even if you are solving problems in C++, if you have a good grasp over C++ and you are attending, let's say, my lectures, then your logic is clear. You don't even have to see the code. You can do it on your own. So for understanding DSA, you can go through any playlist. What we do is, we are following the GFG SDE sheet playlist, and I solve all the problems in Java. Okay, so that's all. Okay, one person is asking, no, I'm not a college student, I am a working professional. I think yes, there's a person with username man. He's saying right, you can choose that course for C++. Definitely, since there are not many courses with Java, that is why I'm taking Java here as playlist, because it's always good to have a playlist with the language we want to be, so that we don't have to struggle writing it in our own language. That's why we are taking here in Java. Okay guys, then try to do this question. This is a very good question. Very means this question is asked in interviews. So you can ask if you have any doubts. I'll wrap it up otherwise. Shall we wrap it up then? Fine. Thank you everyone. Take care. See you all in the next lecture tomorrow. Bye bye.